Training a neural network, it can feel like you're trying to solve this massive invisible puzzle. You know there's a solution in there somewhere, but actually getting to it, that takes the right tools and a real understanding of the roadblocks. So let's dive in and pull back the curtain on this whole process.
All right, so let's just get right to it. Why is training a neural network so darn hard? I mean, it's not just about throwing more data or more GPUs at the problem, right? Nope. The real challenge comes from the very nature of these deep networks. These fundamental hurdles that can literally stop the learning process dead in its tracks.
And hey, this is not a new problem at all. This quote from Ruo Yu's son just hits the nail on the head. Imagine it's 1980. You're trying to get a neural net to classify images. Your first few attempts? They're probably going to fail, and fail spectacularly. For decades, getting these things to work was way more of an art than a science. It really took some huge breakthroughs to get us from those frustrating failures to the incredible models we have today.
So here's what we're going to do in this explainer. First, we'll tackle the core challenge, this idea of an optimization landscape. Then, we'll get into the nitty-gritty, like the learning rate dilemma and this kind of weird thing where neurons can literally die. And to wrap it all up, we're going to arm you with a practitioner's toolkit, the stuff that actually makes training work in the real world.
Okay, so at its absolute core, training a neural network is just one big optimization problem. We have this thing called a loss function, which is just a fancy way of saying it measures how wrong the network is. Our entire goal? Tweak the network to get that wrongness score as low as possible. And the best way to picture this is to imagine you're trying to find the absolute lowest point in this massive, ridiculously complex, and totally invisible landscape.
Let's stick with this landscape idea for a bit, because it's super important. This is not some nice, smooth ball where you can just roll down to the bottom. Oh no, think more like a crazy mountain range filled with 1,000-foot cliffs. Those are exploding gradients, and then these vast, perfectly flat deserts are vanishing gradients. Just figuring out how to walk through this terrain, well, that's pretty much the central challenge of all of deep learning.
So what exactly are these gradients? Well, the gradient is basically the direction to go downhill. It's the signal that tells our network, hey, adjust your weights this way to get a little bit less wrong. Now, if that signal suddenly becomes massive, if it explodes, the network takes this huge chaotic leap into who knows where. And if this signal shrinks down to basically zero, if it vanishes, the network just stops. It doesn't learn anything. Either way, it's a total disaster for training.
And this simple graph shows it perfectly, just in one dimension. See that super long, flat part in the middle? That's your vanishing gradient. If you land there, you're barely moving, because the slope is almost zero. It'll take forever to get anywhere. But then look at the sides. They shoot straight up. That's your exploding gradient region. One tiny wrong move there, and you're launched into orbit. And our goal is to somehow navigate all that chaos to find that perfect little minimum right there at w equals 1.
Okay, so if the landscape is this crazy, it begs the most practical question that everyone who's ever trained a model has to ask. How big of a step should you even take? Right? What's the right step size for this journey?
And that's exactly what the learning rate is. It's our step size. It's just one little number, usually something small, that decides how much we adjust the model's weights on each update. Sounds simple, right? But oh boy, getting this one number right is an incredibly delicate balancing act.
And here's the classic dilemma. If your learning rate is too small, you're taking these tiny baby steps. You'll make progress, sure, but it'll be painfully slow, and you could easily get stuck for good on one of those flat plateaus. On the flip side, if your learning rate is too big, you're taking these giant, clumsy leaps. You'll just jump right over the minimum, again and again, bouncing around like crazy and never actually converging on the answer.
So if one single fixed learning rate is so tricky, what do? Well, we get smart about it. We use something called a learning rate scheduler. The idea is simple. Instead of picking one step size and sticking with it, we make a plan to adjust it as we go. Let's take a look at a few popular ways to do this. The general game plan is pretty intuitive, right? You start with a bigger learning rate to cover a lot of ground quickly when you're far from the solution. Then, as you get closer, you start shrinking the learning rate, taking smaller, more careful steps to really zero in on that minimum. You can shrink it in a straight line, which is linear decay, have it drop off quickly at first, which is exponential decay, or cut it by a certain amount every few epochs, like a staircase, which is step decay. They all help you fine-tune the model at the end. All right, now let's zoom way in on a really specific and kind of fascinating way that networks can fail. It's a direct result of those vanishing gradients we talked about, and it has a great name, the dying ReLU problem. So here's the deal.
The most common activation function out there is called ReLU. It's super simple. Positive numbers go through, negative numbers become 0. That's it. But here's the catch. If a neuron gets hit with a big update that pushes its output into the negative zone, well, it starts outputting 0. And if it keeps outputting 0, what's the gradient of 0? It's 0. And a 0 gradient means 0 updates, which means 0 learning. The neuron is toast. It's effectively dead and is now just taking up space in your network.
So, to fix this, people came up with some really clever tweaks. You've got leaky ReLU, which, like the name says, allows a tiny bit of negative signal to leak through. It's not 0, so the gradient isn't 0, and the neuron stays alive. Then there's parametric ReLU, or PLU, which is even cooler. It lets the network learn how big that leak should be. And finally, ELU uses a smooth curve for the negative part, which can help learning along in other ways. But at the end of the day, all of these are designed for one simple reason, to make sure our neurons never completely flatline.
Okay, so we've talked about the big, scary landscape and dying neurons. Enough problems. Let's talk solutions. It's time to open up the practitioner's toolkit. These are the powerful, proven techniques that have become the absolute go-to methods for making sure your models actually train properly.
I want you to think of these next few things as our gear for conquering that wild optimization landscape. We're talking about stuff like initialization, which is all about choosing the right starting point for our climb, and normalization, which is like having a guide that keeps us on a stable path. These aren't just tricks. They're tools designed to reshape the problem itself, making it easier to find a great solution and find it way faster. First up, initialization. Where you begin your journey matters. All what? You wouldn't want to start a hike at the bottom of a ravine or on the edge of a cliff, right? Same idea here. The goal is to start in a good spot in the landscape, not one that's already unstable. Smart initialization methods like Xavier or Keiming are just clever ways of setting the initial weights so that the signal can flow through the network properly from the get-go. It gives you a huge head start. Okay, next in the toolkit, normalization. So if initialization is picking our starting point, batch normalization is like a course correction we do during the journey. After each layer processes a batch of data, the distribution of its outputs can shift around. This is like the ground constantly shifting under your feet. Batch norm steps in and just recenters and rescales everything, putting the ground back on solid footing. This makes the whole landscape much smoother to navigate, and this is a huge bonus. It often lets us use a much higher learning rate without things blowing up. And finally, sometimes the best tool is to just change the map itself. That's what architectural changes like skip connections do. This was the big idea behind ResNet, and it was a total game changer. All it does is take the input to a block of layers and add it directly to the output. What this creates is essentially a shortcut, an information highway for the gradient. It can just bypass all those layers and flow straight back, which basically solved the vanishing gradient problem for even ridiculously deep networks. So, if there's one thing you should really take away from all this, it's that these techniques, smart initialization, batch norm, skip connections, they're not just random tricks people stumbled upon. They are elegant, principled solutions that were specifically designed to fight back against the core mathematical challenges we've been talking about, to tame that wild landscape of deep learning. And that's our toolkit. Now you have these weapons in your arsenal, from managing your learning rate and choosing smarter activation functions, all the way to using better architectures. You're ready to face these challenges head on. So I'll leave you with this question. For the next model you build, which one of these problems are you going to tackle first?